Since I was asked whether I've ever seen a prograde wall modes, and I said, no, I haven't. And Bob nicely reminded me that I actually wrote in a paper that I had. So I think that's your joke, Mike. This is one simulation that I've done some time ago. It's a low Rayleigh number, Prandtl 0.8. And what you see is that this one is at Rossby 0.3, Rossby 0.5, both shown temperature fields. And what you see is that one is rotating prograde and the other one is rotating retrograde. You can actually tune the Rossby number to make the mode completely stop. I think the main question is this really a wall mode or is it maybe an oscillatory bulk mode? But maybe it's a wall mode and then it's prograde. And then it's for small aspect ratios. So just to clarify that. But in a large aspect ratio, and that's clearly a wall mode, I've never seen a retrograde wall mode. Prograde wall mode, sorry. Okay, so now to my actual talk, so which has a very vague title. But what I'm actually planning on talking about is something that I've also been discussing with Keith, which is Prandtl number dependence of rotating convection. And Keith kept on asking me the question whether I think that if I go to really extreme parameters, does it really matter that my Prandtl number varies in the simulations, or whether I could still tell if I'm in this extreme regime which Prandtl number I have. And he never really gave me a clear answer what he thought. I think he tended towards probably it becomes Prandtl number independent. But I always thought, okay, I can still, there might be that a heat flux and momentum is independent of the diffusivities, but I would believe I still see a difference. I will try to convince you that it might matter still, but then we are not really at geophysical and astrophysical parameters. So, but that's really kind of the main part of my talk. And the reason for that is we already know we are here for trying to understanding geophysical and astrophysical fluid dynamics. And as you've seen in John's word cloud, it's rotating convection. So that's why my talk will be about rotating convection. And what we know is that both on Earth, so where we have the atmosphere with a Prandtl number of 0.7, we have oceans where the Prandtl number is more corresponding to water. And then, of course, we have the outer core where should I use the pointer maybe? Where, of course, we have a liquid metal. And then if we go to more systems that are outside of our Earth, so for the Sun, for example, our Prandtl number is expected to be much smaller, so more out of the order of 10 to minus 6. One example that I'm going to talk about in a bit more detail is where the Prandtl number is around 1, and it's usually simulated with a Prandtl number around 1. But what I'm trying to show you is that actually the Prandtl number varies at least throughout the molecular envelope, and that might actually have an effect on the flow. And then, of course, we have also ocean worlds, where, of course, we would also try to figure out what's actually going on in, again, which would probably be similar to what we have on Earth. But what we try to do is with numerical simulations is we try to figure out what's fundamentally going on, and I'm more, like John would say, on the side of the fluid dynamics, trying to get what's the fundamentals here. And one of these things for fundamental fluid dynamics is that we really try to collaborate with experiments, we try to put in the theory, and then I'm more on the numerical side. But all of these things need to work together, and there's usually, if you work together, then there's some synergy and we actually figure things out. So that's the main thing, and that's also why it's important to design numerical simulations that not just fit to a geophysical system, but that actually also fit to experiments, which then comes back to Rudy, where I will also show simulations of cylinders, so which are good geometry. But maybe first, just some little overview, because Alban and I have done that recently for experiments where we looked at the different geometries that you can use. So, and I thought, oh, I do the same thing for numerics. So, and what we can do is, of course, the obvious choice, if you want to model planets, would be to go for spheres and spherical shells. which you see here on the very left. And this would be in numerics. It's relatively easy to do. We don't have any issues here. We can have our gravity being a central force field. Experimentally, of course, it's more of an issue. Then we have the more difficult system of periodic Cartesian domains, but which is maybe not that relevant or not exactly relevant because it's periodic and does not really exist in real systems. But it's a very useful system if you want to compare to theory. And then there's the Busse annulus and there are cylinders. And of course, all these systems have pros and cons. But as John and Thomas Gastin have shown, is that actually all of them are kind of relevant and that we can also use them to understand what's going on in geophysics and astrophysics. And what I try to do is, probably all of you have some other ideas about it, is what is actually a pro and a con of all these different simulations if we do them. So for example, here is the simulation of Thomas Gastin. I think this picture has been used very frequently. And of course, a big pro of the spherical shell simulation is that it looks like a planet. So that's obviously a pro. We also know that there are lots of open codes available, that everyone who wants to do numeric simulations can use them, like Magic, Rayleigh, Daedalus. And then on a con, of course, it's numerically more expensive than if you would do a nice local model, if you would just use a cylinder, for example. And one of the big problems, of course, is if you think about synergy with experiments, experimentally, it's really hard to do. So either we use an experiment that Seth Putterman is using, where we have a spherical geometry, or the other alternative is we go to space. So these are, I think, the only experiments where we have actually a central force field. And then we need to use other forces. And then what is both a pro and a con for spherical geometries is, of course, we have the curvature, so which means we have different effects that just come from a geometrical effect. So is that really what you want to have when you want to understand fundamental physics? Of course, if you want to go for a realistic system. But if you want to look at it more from a fluid dynamic system, it's much harder to understand what's going on versus if you had a plane layer. And then also we need to somehow de-entangle what's going on in the equatorial region and what's going on in the polar region. And then the other one is periodic domains. The nice thing about them is, so this is from simulations from Song, but I think there are also lots of simulations from the group around Keith Julian. Mike has done some. So which is, if you have periodic domains, the nice thing here is we can reach more extreme parameters than probably in spherical shells because it's numerically much cheaper. One of the nice things is this is one of the domains where we've seen large-scale vortices, which we hope are relevant for geophysics, and we have inverse cascades that we can nicely study. We can, or all the asymptotically reduced models, or most of them, I think there are also some in spheres, are in more periodic domains. And on the negative side, of course, is a periodic domain, and an experiment is really hard to do. And then also one needs to be very careful about the influence of horizontal periodic boundaries, probably less in rotating flows. And then in experiments, the Busse annulus is very popular. Interestingly, except for Mike, who has looked at in reduced model of this, I've actually not found any proper numerical simulations of the Busse annulus, even though it is very nice, actually, because you can study the beta effect, study Rossby waves, zonal flows. And you have really good experimental data available, but no one has actually done a proper DNS, as far as I can tell, with the sloping end walls. So these are just numerical simulations where we have a flat end wall, and these are actually even periodic. So, of course, the obvious con is it ignores the polar region, so they are just a model of what's going on in the equatorial region. And one of the problems, I guess, why people are not doing this is because it's probably numerically challenging to get the sloping end walls and to get something that is more as a model for spherical convection or spherical equatorial convection in. So, and then, as we've heard probably several times, so this is a nice picture by Jewel Abate, and this is the cylinder. It's my preferred geometry. I think it's nice for simulations, it's nice for experiments, and it's really nice because we can work together, and it also means we can look at the same parameter space and have some synergy effect here. It's less demanding than spheres, obviously, because we are essentially just modeling here this little bit in the polar region. What?
I like that you have the Walmart as pros and cons.
Yeah, I mean, I think that's the outcome of your talk too, right? So the obvious con is, in this case, we are just focusing on the polar region because that's where the rotation axis and gravity are essentially aligned. Numerical, there are a few codes that do a really good job, but otherwise, typically, it's quite challenging because you need to deal with the cylinder axis, for example, because that's mathematically not so nice to deal with, but they actually work. And yes, wall modes and cylinders, we have walls, and so they're very nice to study. We will have several talks on wall modes by Bob, and I think by Edgar and by Rudy. We also had already a lot of talk about the wall modes. And it's, as we have heard, debatable. Are they useful? Are they geophysically relevant? So for example, Alban has seen them in experiments of the tangent cylinder. So that would mean they are relevant geophysically. And yet there are lots of plans to actually get rid of the wall modes. So, and what I said is, maybe that's also, should say that, is that if we want to really couple with experiments, so what we have done is we have nicely mapped out how experiments span the parameter space. So what you see here is essentially, this is roughly where Earth sits. For the estimate for the Rayleigh number, Ekman is 10 to minus 15, as you've heard. And if we look at axial gravity, so this would be cylinders and also box geometries, what you see is they span actually a quite big parameter space. So that's probably the most useful geometry if you want to really compare to experiments. This is analyst geometries, so they are also relatively big. Then specifically a bit tangent cylinder, which are also cylinders in a way, but consider also the effects of the tangent cylinder. And then if we look at spheres, what we see is they are really farthest away from Earth. So which means that if you want to compare to experiments, maybe they are not the preferred geometry. They are preferred geometry if you want to compare to planets, but definitely not if you want to couple to experiments. Okay. So, and that's why the rest of the talk, almost all of the rest of the talk will be on cylinders, because again, nice for experiments. And so I will start with just normal rotating convection. These are just the Navier-Stokes equations. Main thing is I numerically solved them with goldfish. And what I want to say. So in this case, I ignore centrifugal buoyancy, even though centrifugal buoyancy is technically in there. And later on, I will also show a bit effects of the magnetic field. So that's why this is a bit grayed out. But for now, very simple setup, cylinder, heated from below, cooled from above, like the standard thing. And now coming back to my original plan, which is discussing really, does it matter which Prandtl number we choose for rotating convection? Because if we look at most simulations, then the Prandtl number is quite often set to 1, especially in spheres. There are very few exceptions where really a broad parameter space is spanned. And in experiments, also the Prandtl number, most frequently, it's greater than 1. So like what Rudy showed, these were all water experiments. So in very few actually vary a lot in parameter space. John and Jewel Abate have done a nice study, but also this was for Prandtl numbers larger than 1. So, and liquid metals are kind of the only exception. And this is also essentially just the repetition of what John has shown already. And this is, if you want to consider the Prandtl number dependence, of course, the first thing you want to look at is what's the onset of convection. And what we see is the normal or the naive onset of convection is stationary, so that was based on Chandrasekhar, and that's really valid for all Prandtl numbers larger than 0.68. And what we get is the typical Prandtl number, critical Rayleigh number that scales with Ekman to the minus 4/3. And for our length scale, we get an Ekman to the 1/3. And the most important thing is this is independent of the Prandtl number. So at onset, we get cellular structures. And then if we would go to a more nonlinear regime, then we will end up with Taylor columns. But the interesting thing is they keep on scaling essentially with the onset scale. So, and this is also strongly dependent on the viscosity. So that's also why, so the onset is essentially the viscous mode. And then if we now actually look at other Prandtl numbers, so less than 0.68 specifically, so that comes out of the linear stability. And also John mentioned that already. Then we have oscillatory convection. The main thing is that the scaling with Ekman is actually also minus 4/3, but it now has explicitly a Prandtl number dependence, which means the viscosity drops out here. The same for the length scale. Also here, we have Ekman to the 1/3, but it's now the thermal Ekman number because it's Ekman over Prandtl. And what that means is that we have a lower onset if we have small Prandtl numbers, because if we compare that, this will depend on the Prandtl number. And if we compare our length scales, what we will also get is that we have bigger structures, which depends on the Prandtl number, but again, the Prandtl number is small. And the interesting thing about oscillatory convection is that unlike stationary onset, which turns into these nice columns, is that we have a lot of modes that become very quickly unstable. They interact nonlinearly, so which means we have very quickly a turbulent flow at much lower supercriticalities than what you would expect in a high Prandtl number fluid. And that makes it a really interesting system to study and also very different to the high Prandtl number fluids. And then what you've already seen, so I will actually not really go into that because that has been discussed in much detail. So we have wall modes, and then if we look at them non-linearly, then what we will see is that if we go to these systems, we still have wall modes, or one could also call them boundary zonal flows. So, and the question that I wanted to ask is essentially, what is the correct control parameter now in turbulent rotating convection? So also this was already in the intro talk. So and essentially, if we now also consider that we have the Prandtl number, what we want to usually do is we want to collapse our data. So what should we vary in the simulations? I think that's one of the big questions. What should we keep fixed? Should we go constant Rayleigh number, vary the Ekman number, or should we really vary the convective Rossby number? So there are different studies, depending on which field you are in. If you look more in the fluid dynamics community, all the plots are versus the convective Rossby number. If you look in the more geophysical community, all the plots are versus the Ekman number. And is that really the right question to ask, and what determines the regime boundaries? And what we know, however, is that essentially both the Ekman number and the convective Rossby number, they need to be small. Rossby for small means typically less than 0.2 to be rotationally constrained. At least that's what Keith concluded in 2012, that this is a good measure for the convective Rossby number. And for the Ekman number, what is small, probably at least 10 to minus 4, but probably rather more 10 to minus 6, 10 to minus 7, if you want to go to a really rotationally constrained regime. And then the alternative is, of course, maybe it's not the right parameter. So what we have also seen quite often, what collapses the data is to actually look at supercriticalities. But what I've shown you before is we have actually several supercriticalities. We have the wall mode, we have the oscillatory modes, and we have the stationary modes. So which would mean that maybe there are different regimes based just on the supercriticality. So, but what all of these criteria kind of only have implicitly in is the Prandtl number, so does it really matter? And what I've tried to do is to actually just show you some essentially interesting flow field. What are the onset predictions if we fix one of the control parameters, namely if we fix Ekman? It's not that small, so it's 6.6 times 10 to minus 5. And if you have a fixed Rayleigh number, and what we see here is that essentially this would be the yellow is the stationary onset, we have the wall mode onset, and we have oscillatory onset. And I'm wondering, did I flip that? But what we see is that essentially if we go to small Prandtl numbers, so this is really over really critical versus Prandtl, is that if we, no, it's correct, sorry. If we go to small Prandtl numbers, what we see is the onset essentially is via oscillatory convection. So because it's really over really critical, it's not really critical. So, and that means then there comes the wall modes and then come the stationary modes. And only here, so in this regime, we would expect that there is a huge influence of the Prandtl number on what the type of convection that we see, versus if you're on this regime, you would first have the onset of wall modes, so that's why they are strongly supercritical, versus the stationary modes that have a much lower onset. So that's really the main thing. And if we look at different flow fields, so varying from Prandtl 0.0.1 to 2500, so with a few examples, so here we have gallium, here we have roughly air or SF6, because these are the experimentally relevant one. Here we have water at 40 degrees Celsius, so it's 4.38, and we have glycerol. So these would be experimentally accessible parameters, and then of course some generic ones like 1, which would be the typical one that is used in many of the spherical simulations or generally in simulations. And what we see is that clearly we don't get quite the same answer in terms of what we see, because what we see here is, yeah, we have the typical convective Taylor columns for the high Prandtl number fluids. So, and also if you would plot heat flux, etc., that would actually collapse very nicely. But once we go to smaller Prandtl numbers, we have here oscillatory modes, which is strongly supercritical. In the temperature field, it's less visible, but in the velocity field, what we would see is that we really almost reach free-fall velocities, and our structures are clearly very different than what you would get otherwise. And that's the case, even though stationary onset, again, is for all the simulations have the same supercriticality. But what it also shows is that in these cases, it seems like oscillatory modes really dominate over whatever happens with the stationary modes, at least for these relatively low supercriticalities. And then we can also, of course, go the other way, so which is more the fluid dynamics viewpoint, is we now keep Rayleigh still fixed, and also now the convective Rossby number or adjust the Rossby number and keep it fixed to 0.1. So at least from that perspective, we are rapidly rotating. And if we now plot our onset predictions, it now suddenly looks as if everything is Prandtl number dependent, which comes, of course, from the fact that all our onset predictions are dependent on the Ekman number, and the Ekman number implicitly, of course, depends on the Prandtl number if we keep Rossby fixed. That makes sense. And what we would see is also that essentially, if we go to high Prandtl numbers, they are strongly supercritical if you keep this fixed to the stationary modes. But if you go to lower Prandtl numbers, you would just have oscillatory convection. So, and if we cross now the parameter space through this, what we would get is also that clearly this is not really the same thing that we see in all the flow fields. What you might still see is that if we go to moderate Prandtl numbers, so because this is essentially the reference case that I used, so I used water, so it's the same Ekman number as we had before. But what you now also see is the Ekman number varies because the Rossby number is kept constant. So this is now only Ekman 10 to minus 3 in glycerol. So clearly this is not rotationally constrained. And while here we have really low Ekman numbers, we have a low Rossby number of 0.1. But the problem is we are only supercritical now to oscillatory convection, which has a very small influence on the temperature field, at least initially. And then what we see here is also some nice wall modes that start to kick in that we actually see here for most of these cases. But essentially the point I'm trying to make is, at least for these, yeah.
So something that John pointed out is that there's two Rossby numbers. There's one which is the input and one which is the output.
Yeah.
So here, of course, it's easy to fix the input one.
Yeah.
So how much does the output Rossby number change across these? And what if you fix that?
I think it's very hard to fix an output parameter. I think you can only do this afterwards. So, but the interesting thing is if we go to liquid metals, if you go to small Prandtl numbers, you very quickly reach free fall velocities in your velocity. So while this is much harder if you go to high Prandtl numbers. So I think it would be interesting to see whether this looks similar or not. I haven't done it, but this is what I can tell you. But I think Jewel, I'm not sure what came out of your paper. So she has done it for high Prandtl numbers, but I think no one has done it for high Prandtl numbers and low Prandtl numbers. Is Jewel actually here? Shouldn't Jewel be here?
She might be here later in the week.
Okay.
She's got pretty good predictions at low now and high Prandtl. So technically, we could invert what she did and try to do studies at fixed Rossby. It's a nice idea.
Yeah.
It wouldn't be that easy to do, but we could get pretty close with her scalings.
So my point is essentially neither Rossby nor Ekman, at least for these less extreme parameters than you maybe have in Earth's core or generally in geophysics and astrophysics. Here the Prandtl number definitely still matters if we use this as just a control parameter. And the interesting thing is, I think John also already showed this paper. So there's a nice paper recently, 2024, by Wei Fan et al. And so what they have done is one of the few studies where they actually also vary the Prandtl number in spherical shell convection. Unfortunately, at least in their paper, they only gave the results for Prandtl 0.01 and Prandtl 7, but they actually went up to Prandtl 100. And what you see here nicely in spherical convection is what's mentioned before, that for initially you have an onset only in the equatorial region, while you have nothing going on in the polar region. One of the interesting things is also that here the non-viscous mode, so the thermal inertial mode or the oscillatory convection mode, scales slightly differently. So with Ekman, I think it's Ekman to the -1. And this is more the intermediate mode, which is spiraling convection. And what they argue is essentially that if you go to low Prandtl numbers, what you would find is that also in this regime, for low Prandtl numbers, you would get a diffusivity-free scaling both in the heat transport and the momentum transport, while it's much harder to reach that for high Prandtl numbers. But what the interesting bit is that the weakly rotating regime, maybe that's similar, but what you have here, they argue there's geostrophic turbulence in the sphere where we have these nice aligned structures. They look really, at least to my eyes, differently if you go to a low Prandtl number. So you can, at least I can still see the difference, even though it's supposedly in a regime where they argue that you have a diffusivity-free scaling. So for me to answer Keith's question, yes, I can still see a difference between these two simulations, even though the heat and momentum transport are supposedly getting to diffusivity-free scaling. And that seems to be also the case for spheres. Yeah.
Sorry to keep on harping on this. Is this the input Rossby number or the output Rossby number that you're?
In my talk, it's always the input. So it's always the convective Rossby number. I think that's true for almost all papers that you find from the fluid dynamics community. But what it also really means is maybe Prandtl 1 in spherical simulations is not the answer. So we have lots of data, but I think we should also consider what's going on for small Prandtl numbers in spherical shells. And which then also comes back to these experiments in liquid metal, and where we look at oscillatory convection is probably really useful. So maybe as a little bit of a short summary of that, the effect of the Prandtl number really is non-trivial. I hope I could convince you of that, at least for the parameters that we are now. And apparently also if you go to more extreme parameters and if you go to the sphere. The main thing is that once we have oscillatory convection in small Prandtl numbers, and we only have that in small Prandtl numbers, it's then multimodal. We see that at relatively low supercriticalities, at least if we compare it to high Prandtl number fluids, we approach a diffusivity free limit, or also CIA scaling. And it really remains to be decided how long this Prandtl number dependence exists and whether it's actually still important or whether Prandtl 1 is the answer. And one example that I wanted to show that really, in my opinion, matters is for gas giants. So this is more an introductory slide. So what you know is that almost all the gas giants, we expect that we have different layers. And what I'm mainly interested in is the outer layer, so the molecular hydrogen envelope. And since I'm doing cylinders, so I will just consider a nice little polar region. And what I'm trying to show you is a nice model where we ignore all the effects of magnetic fields so far, and where we also have different boundary conditions that kind of account for it, so that we have a no-slip boundary condition at the bottom and a free slip at the top. And if we look here at our variation of the material properties for the diffusivity, so that's the blue line, thermal diffusivity, and for the viscosity, so that's the yellow line. And then if we calculate a Prandtl number just in the oscillatory in the molecular envelope, what we see is the Prandtl number varies quite a bit through that region. And if we use our plane layer estimate, which we can do in the polar region, what we see is that we have areas where the Prandtl number is above 0.68, and we have areas at the bottom and at the top where it's below 0.68. So this is typically where people say, oh, this is maybe where the dynamo region starts. So, but this is a system where we have essentially regions where we would allow oscillatory convection and where we don't allow it. So, and what I've done is I've come up with several models how to essentially go through end mapper cases. So here, for example, our Prandtl number very similar to where we have the entire region by just prescribing them. I've also then ignored viscosity because that seems roughly constant, so I then just vary the thermal diffusivity. And then where we have end member cases, essentially where on one side here, Prandtl is 0.025, it would be more liquid metal. At the mean temperature, it goes to 1, and at the bottom temperature, it goes to 2.5, so it's more water-like. So, and again, that would kind of mimic what we would expect in the envelope, so that we have regions where we are above 0.68 and below 0.68. And then in this case, the nice thing about numerical simulations is we can actually put in all arbitrary variations of the material properties, so that it's relatively easy to do, especially in a finite volume code. The same as that we can keep them constant, which is much easier to model than in experiments. That's usually more of a problem. And if we do that, and we take our nice estimates, what we get for these different simulations is that we have different regions. So all these purple regions are areas where we would expect oscillatory convection. And what we see is that here we have oscillatory convection at the top. Here we have oscillatory convection at the bottom. And here we have two cases. So this is the one where the viscosity also varies a little, where oscillatory convection essentially sandwiches steady convection in between. So the main thing here is that, of course, that causes then so-called non-Boussinesq effects, because we are now moving away from that. And what we can see is that in some of the cases, so we have suddenly a much higher temperature in the bulk, and in other cases we have a much lower temperature. And I will just skip over that because Kai has a poster on some of this. But what we can do is you can use these temperature profiles to actually get a nice realistic predictions for that, but it's very similar. But what I just wanted to show you is that also here in this case, we essentially now have a locally varying Prandtl number in our system. So and what we see here is this would be what you would typically expect in Overbeck-Boussinesq simulations, where these material properties are constant. Here's where we have oscillatory convection at the top and bottom. And what you would see is that convection seems to be really, or steady convection is confined to the center. And then what we also see is we can actually, with that, tweak a bit the wall modes. What we should see is that, for example, here we have wall modes only in the top part. Here we have wall modes at the bottom part. What you see here is nice. I hope you see it. You have the stationary convective columns in the center. But throughout the simulation, the material properties clearly vary, and the Prandtl number varies, and we see a difference, at least in this parameter space. And then, really a bit short on time, is that, so if we take our typical Hofmüller diagrams, I think you see the same thing. So this is just the temperature field, where you would have, for the case where you have water-like fluid at the bottom, you have nice columns that kind of poke very far into the bulk. On the other hand, because we have a free slip layer, it is less efficient in doing so in the other way, if you do the other simulation. And for the cases where we have oscillatory convection at the top and bottom, what we see is that this also leads to a stronger variation of the temperature, but otherwise it's actually quite similar. It's more extreme if we look at the turbulent kinetic energy. So what we see here is that kind of if you have these nice columns in the center, this is now vertical velocity, we can actually get transport towards the bulk. On the other hand, if it would be the other way around, it's less efficient. And overall, what we also see is if we have oscillatory convection at the top and bottom, versus in the Overbeck-Boussinesq case where we have nothing, our turbulent kinetic energy overall goes up, which means it would support transport really of heavy elements, at least if we use this as a proxy. So, and because we have a free slip layer, a free slip surface, we can also look at how it affects flow structures for these different cases, and where we see is really, it would matter in what we see at the surface of the planet. And this, at least based on this very simple model. And it would change the size of the structures that we observe. So that's just like this very quick example where I would argue matters.
I had a question. I probably missed it earlier. How did the Prandtl number vary with height? Or did it vary with height at all?
So it varied with temperature. I've also done simulations. Yep, here's it. So there are different cases. So this is the Prandtl number that varies with the temperature. But I've done also cases where essentially instead of using the temperature, where it varies with the height, which would mimic kind of like what if your material properties are pressure dependent, like as a nice proxy. And you get a similar answer, but I would say the effects are slightly less extreme than if you
vary with temperature.
The effects are more extreme if you vary with temperature versus with, yeah. So what the interesting bit about this here is that we get if our Prandtl number varies throughout the fluid, like it's the case in molecular envelopes of gas giants, then we would expect that there are some thermal inertial oscillatory layers. The spherical simulations also show that it actually matters, so it might really matter in the entire planet. And that might really affect how momentum is transported. Of course, only if the simulations that were at not very extreme parameters carries over to geophysical parameters. And then maybe just as a little close-up, because it's not just the Prandtl number that matters in geophysical systems, but what we can also do in numeric simulations is we can look at MHD effects, because in the end, you're also interested, for example, in planetary cores, where the magnetic field matters. And then in this case, we have a liquid metal, and we have oscillatory convection, and we should focus on what magnetic fields do. So, and I just wanted to show you that our life becomes much harder because we have now many more modes that are stationary. So these are not just the geostrophic modes, which would be this line here, but now we can have onset modes that are magnetostrophic or magnetic. We still have the wall modes, so that's the interesting bit. But these wall modes can now also be either here magnetostrophic or they can be magnetic. They would still be the preferred onset behavior in these systems, except for oscillatory modes here. So probably even in magnetoconvection, wall modes still matter, not just in rotating convection, so maybe also in planets. And if we take the model that I'm going to use, which is really just externally applying a field, not a dynamo, then the oscillatory modes are, however, only for smaller Alsacer numbers. Maybe I should say that. So the Alsacer number compares how important is rotation compared to how important is the magnetic field. So which means if our Alsacer number is less than 1, then it's mainly rotation. If our Alsacer number is larger than 1, it's mainly the magnetic field that matters. And so what the interesting bit here is now that with magnetic fields, you might expect to get also larger structures. So which is also one of these big questions is it actually relevant that we do all these simulations of rotating convection? Is that really what matters in planets? Or will we get larger length scales? And what I wanted to show you is just that once we start to also vary our magnetic field, our possible range of flow structures that we can get and we try to understand it becomes really much bigger. So what you see here is different Alsacer numbers. So essentially we are increasing the magnetic field from left to right. And then some are at the boundary layer, some are at half height. And this is showing temperature fluctuations versus the vertical velocity. And maybe one of the interesting bits is here that we get nice wall modes that essentially stop to drift once our Alsacer numbers is high enough. And what we would also see is here we have oscillatory convection with out wall modes. Here we have oscillatory convection with wall modes. And then we have the magnetic structures that essentially, if we go to extreme cases, are a bit smaller than oscillatory convection. And if we go to the interesting range, which is usually around Alsacer 1, what you would get is still an effect of oscillatory modes overall on the flow field. And maybe just to show that a bit in a movie, so this would be what people usually argue is the geophysically most relevant case because it's around Alsacer 1. It's based on, so it's trying to match the experiments by Nakagawa. And I think Alban is going to talk much more about magnetic fields and also a bit about the experiments in his next talk. But the interesting bit here is what I want to show is, so this is the strongly magnetically dominated case. And all these simulations are running at free fall time at the same speed. But what you should hopefully see is that if we compare this case to this case, so these are magnetostrophic modes, and they are very slow, while here we have magnetostrophic modes and oscillatory modes, which means, and what you hopefully can see, is that they move much faster because also here what we see is that once we have oscillatory convection, we at least seem to approach diffusivity of free scalings, even though we are really close to onset. So that's really the main thing about small Prandtl numbers. And if you would extrapolate that to Earth, then of course you would see we have larger length scales. So as you might see here, these are the geostrophic modes. The magnetostrophic modes would be much bigger, so 5 orders of magnitude difference. And really the question is, if we go to Earth, which is here in the purple area, roughly where planets sit, is it then still important that we have oscillatory convection? Would they still dominate? We still have a much more efficient momentum transport. So brings me a bit to my conclusions. So if we use numerical simulations, we are able to essentially get rid of all the complications of experiments and idealize our system. We have perfect control over our equations. And one of the important things, I think, is that we have also full flexibility in varying our Prandtl number and to systematically explore it. And I think that's also one of the things that we should really focus on. What's the influence of the Prandtl number? The nice thing about the cylindrical simulations is that we can compare to the experiments. But of course, the open question is, so this is essentially Keith's question, does it really still matter once we go to an ultimate turbulent regime, diffusivity-free regime? Does the Prandtl number dependence still matter? And also, does the variation of the material properties in a layer matter, which would be relevant for gas giants? And then, of course, the question is, people argued that the high Prandtl number systems are really relevant if we look at compositional convection. So really, what about double diffusive convection? And then also, what we do with experiments with numerical simulations is we look at magnetoconvection, but is that actually really relevant if we consider a proper dynamo? And then maybe another question that is only related to numerical simulations is we don't really know how well should we resolve and what are actually effects of numerical resolution, which I think also one of the issues that we should still solve for numerics. And I think that's it. Thank you.